Okay, so we're happy to have Udit Mavinkurve from Western University, who will talk about fibration category structures for the discrete homotopy n types of graphs.
Thank you for the introduction and for the kind invitation to speak. And thanks for everyone attending. I'm happy to talk about this work. So based on my joint work with my PhD advisor, Chris Topology, and these are the two archive preprints that form the original research that I'm going to talk about. And of course, there's a lot of other mathematicians who have been working in discrete homotopy theory that we're building on. So it's always we're standing on shoulder of giants as always. So I want to talk about, start with just the outline of the talk today. So I want to begin by just giving an introduction to discrete homotopy theory and maybe invite you all to, or at least make the pitch that there are a lot of open problems that people can make contributions to. And I hope that there'll be more people working in this area. And then I'll get to the title. I'll start addressing the title. So I'll give a brief background of fibration categories. So I believe, I think in the seminar, there was recently a talk about model categories. So fibration categories are an alternative framework for doing abstract homotopy theory. And then I'll get to specifically fibration category structures for the homotopy types or the homotopy infinity types of graphs. And then we're going to look at homotopy n types of graphs. Okay, so let's begin. So what is discrete homotopy theory? So as I was saying a bit before the recording began, so the field of discrete homotopy theory really arose from very applied considerations in Q analysis, which is the work of this mathematician Atkin. And then it was really distilled into this theory about graphs, so homotopy theory designed for graphs. And the key distinction between the classical treatment of graphs in homotopy theory versus the discrete treatment is that it really respects the discrete nature. So in the classical treatment, graphs are treated as one-dimensional CW complexes, but then your maps are still continuous maps, and then your notion of homotopy is also continuous. So the homotopy theory of graphs as one-dimensional CW complexes isn't particularly interesting. Every graph is homotopy equivalent to just a bouquet of circles, right? So you just get free groups in as your fundamental group, and then it has no higher homotopy groups at all. So we're going to see that discrete homotopy theory sort of naturally produces when you discretize your objects and your morphisms and your notion of homotopy theory, you actually get a much richer theory. And I believe that's the right notion of homotopy theory for graphs that we should be studying. So let's begin by just specifying what graphs are for us. So graph for us is a set equipped with a reflexive and symmetric relation tilde. And we're going to depict graphs as follows. So I think this might be a delay, a lag between my iPad and Zoom. So I hope that's fine. I hope that won't cause too much chaos. But what I want to say is that the elements of the set are represented by these vertices. And then you draw an edge between two vertices every time there's when these two vertices are related under this relation. Now, because your relation is symmetric, your edges are going to be undirected. So every pair oppositely oriented relation is represented by a single undirected edge. And because the relation is reflexive, you also have a unique loop at each vertex that we just hide to avoid clutter, but those are always present. So you can think of these sort of dots as shrunk loops that are present at the vertex. And the correct notion of morphisms for the discrete notion of morphism is a graph map. So it's just a function that preserves this relation. So, and we're going to depict graph maps like this. So suppose you want to depict a graph map from X to Y. This is how we're going to draw it. So X, suppose you have this domain graph X and a codomain graph Y. The way you're going to depict the data of the graph map is you're going to take the domain graph and you're going to label the vertices using the labels of the codomain graph. So for example, in the graph map that's depicted over here, the vertices 0 and 4 are both sent to the vertex 0. Vertex 1 is sent to 1, 2 is sent to 2, and 3 is sent to 3. So that's what this, sorry, yeah.
Okay, first, can you hear me well enough?
Yeah, I can.
Okay. I'm just wondering about transitivity on the equivalence relation. Is that like a path of length 2 or something?
Yeah, so this relation isn't an equivalence relation. It's just reflexive in symmetry. So we're
Oh,
not
okay, sorry.
imposing transitivity. Yeah, exactly.
Okay, thank you.
Yeah. So we'll actually see. I won't be talking about it today, but when you look at the equivalence relation generated by this, so when you add transitivity, then you're going to be looking at paths of arbitrary lengths between vertices. So that's the equivalence relation that corresponds to this edge relation. But yeah, for now, we're just looking at symmetric reflexive graphs. Okay, so this depiction where 0 and 4 are sent to 0, and then 1 is sent to 1, 2 is sent to 2, 3 is sent to 3. This is a graph map because every edge relation is sent to, in the domain graph, is sent to an edge relation in the codomain graph. In particular, observe that this edge is sent to the loop at 0. So you can collapse edges into a single vertex because you have the loop at each vertex, which is hidden. And I'll give an example of a function that's not a graph map. So it's the same mapping, except that now in the domain graph, you have an edge between the vertices 0 and 2. Now, this is not a domain, this is not a graph map because in the codomain, you don't have an edge between 0 and 2. So this edge is not sent to an edge in the codomain. So this mapping is not a graph. So that just to distinguish what is a graph, which functions or which mappings are graph maps and which are not. So the category or the setting that we're going to do discrete homotopy theory is this. So we denote the category of graphs and graph maps by just graph. And so let's look at some examples. And also these examples serve a purpose because when we want to define a notion of homotopy, it involves two ingredients. One is an appropriate notion of an interval. So in topological or in classical homotopy theory, the interval is just the unit interval from 0 to 1. And you also have the product topology. So you also want to take products of spaces. So analogously, you want to take products of graphs. So let's look at the first ingredient, which is the interval objects. So in discrete homotopy theory, you find that there are actually a lot of candidates for the interval objects. So the first one is the finite interval of length n for any natural number n. So this is a graph which has vertices 0 to n. So there are n plus 1 vertices, and then you have an edge between consecutive vertices. So you have n edges between n plus 1 vertices. So these are your analogs of your unit interval 0, 1. So it's compact. And then you also have the infinite interval I infinity, in which you have a vertex for each integer on the real line, and then you have an edge between consecutive integers. So this is the discrete version of the real line. So we're just sort of modeling what we're familiar with. And the reason we sort of need these intervals of different sizes is that in classical topology, when you take the wedge of the unit interval with itself, 0, 1 by 0, 1, that's something that's homomorphic to the unit interval. Whereas, say, if you start with I1, then if you took wedge of I1 with itself, that would be I2. So you need to take intervals of different sizes. And how do you take wedges of the infinite interval? Because there's no endpoint that you can wedge it along. So these sort of pose sort of basic foundational issues when we'll see that as it comes up. And then we also have these cycle graphs, which sort of form the discrete model of S1. So for each n greater than or equal to 3, we have this cycle graph where your vertices are 0 to n minus 1. And then you have an edge between, or you can think of it as a vertex for each element in Z mod Zn, Z mod Nz. And then you have an edge between consecutive integers mod n. So as follows. Okay. So the second ingredient we need is the notion of a product. So the notion of product we'll be using for this flavor of discrete homotopy theory, which is called a homotopy theory, is the box product. So actually, there are only two notions of products that are interesting from the point of view of homotopy theory. One is the box product, which we'll be describing. The other is called the X product or the categorical product, which gives rise to a different flavor of discrete homotopy theory called the X homotopy theory. So we're going to look at this box product today. So the underlying set for the product of X box Y is just going to be the, as you expect, the Cartesian product of the underlying sets, X cross Y. But then we need to specify a relation on this product set. And the relation is going to be as follows. So two pairs, X comma Y and X prime comma Y prime, are related by an edge in the product graph, if and only if the following conditions hold. So, or one of the two these conditions hold. So note that the condition says that it has to be equality in at least one of the coordinates, and the remaining coordinate can be an edge in one of the graphs that you are taking product of. So the prototypical example of this is I1 box I1. So when you take the unit interval or the interval of size 1 product with itself, first of all, it has I1 has two vertices. So I1 box I1 is going to have four vertices just by virtue of taking Cartesian product in the set. But then now you need to look at where do you draw edges? And because we define the relation as being constant in one of the two coordinates, we're only going to get the outer edges, four edges. Whereas if you were taking the categorical product, or if you were to take, if you were taking the categorical product, you would also get the diagonals. So we're not going to work with the diagonals today. We're just going to work with this box product. And that leads to a notion of homotopy. So if you have two parallel maps, F and G from X to Y, you can define a homotopy between them, FH from F to G. So that is defined to be a map from the box product of X with IN for any natural number N to Y that takes the value F at 0 and takes the value G at N. So you want to be able to go from F to G in a finite number of steps. It's important that N is finite. So there's a way to define this using I infinity, where you say that before a particular, so if you use I infinity instead of IN, you would want to say that before a particular number, it always takes the value F at constant, and then after a particular value, it always takes G as a constant. So that ensures that whatever you're doing is happening in finite number of steps. So this is again an important feature of discrete homotopy theory, that you can't, for example, in classical homotopy theory, you can increase the speed at which things move, whereas in discrete homotopy theory, at each step you can only jump one vertex at a time. So it puts some restrictions. And so once you have a notion of a homotopy, naturally that leads to a notion of a homotopy equivalence. Okay, so that is a graph map is a homotopy equivalence if it's invertible up to homotopy. So there has to exist a graph map in the reverse direction, and then you need to have homotopies witnessing both compositions being identity up to homotopy. So let's look at some examples. So the intervals of finite length, IN, those are contractible in this notion of homotopy. So if you look at the unique map from IN to the I0, which is just a single vertex with a loop at single vertex, that is a homotopy equivalence. So that's what we mean by saying IN is contractible. And the way you do that is you can take a homotopy of IN box IN, and where you start with the identity map on IN, and the last step should be the constant map at 0. And at each step, you sort of start removing vertices. So the first one, you have 0, 1 to IN, and then the next one, you go 0 to N minus 1, and then repeat N minus 1. The next step, you go 0 to N minus 2, and then repeat N minus 2, and then you keep doing that until you get to all zeros. So you can shrink IN into I0, or just the constant map at 0 in a finite number of steps. So that's why it's contractible. And I'm emphasizing this notion of finite steps because when we look at the I infinity, which is the discrete model of the real line, where the real line was contractible in classical homotopy theory, whereas I infinity is not, because you can have points that are arbitrarily far from the origin, so you can't move them. So in the real line, you could modify the speed. So the farther you're from the origin, the faster you move to the origin in order to make it contractible. Whereas in I infinity, you can only move one vertex at a time, so you can't get to the origin in a finite number of steps. So it's not a homotopy equivalence. Maybe more surprisingly, when we look at the 3 and 4 cycles, C3 and C4, we find that those are also contractible. So the unique map from C3 and C4 to I0 is also homotopy equivalence. So I'll just, so this is the homotopy between the identity map at C3 to the constant map at 0, and that you can get from one to the other in exactly one step. So because it's a complete graph, you can push all vertices to 0 in just one step. For C4, you need to take 2 steps. So you start with the identity map on C4 at this top level. And then in the first step, you push 2 and 2 and 3 to 0, 1. So you're squishing along one dimension. So you start with a 2 cube, and then, or just a square, C4, and then you squish to an edge. And then you squish along the other dimension to get the constant map at 0. So in 2 steps, you can get from the identity map at C4 to the um, constant map 0.
Can I ask a
And
question?
yeah, go ahead.
How do you like what's the rule for placing the numbers on the picture to know that it's a valid map?
Yeah, so it just needs to be a graph map, which means that edges need to be sent to edges. So the mapping has to preserve the edge relations. So for example, if you looked at this edge 3, 0, that's a valid mapping because 3, 0, which is connected in this mapping, is connected in the codomain C4. So C4, remember, was 0, 1, 2, 3. So 3 and 0 are connected in the codomain. So it makes sense to do this. Whereas you couldn't push it directly, go from this directly to this, because then you would have an edge between 2 and 0, but you don't have an edge between 2 and 0 in the C4. So that's why you can't do it in one step. You need to take 2 steps. So that's sort of encoded in the notion of a graph map, that it has to preserve edges.
So the fact that
Yeah,
three
thanks for the question.
the fact that 3 is connected to 2 is sort of not visible in this picture because you just sort of take 2 along 1 back to 0 and then 3 to 0.
Yeah. It's you don't have to use all the relations necessarily, but you need to make sure that the ones that you're using are relations in the codomain. Does that make sense?
Thanks.
Yeah. Yeah, so there's actually a weird, unexpected feature of discrete homotopy theory, that's C3 and C4, which you would expect to be models of S1, are actually too small to count as S1, essentially. And the reason that's happening is because the example that we had before, when you took the box product of I1 with I itself, you ended up with something that was isomorphic to C4. And so that's kind of the reason why C4 is too small to count as a whole, because your intervals are contractible, so products of contractible objects are going to be contractible. Whereas if you had a pentagon, we're going to see, well, I'm not going to prove it, but you can prove using computing the fundamental group that this is not contractible. It's too big to be able to shrink it in any number of steps. So to prove that, we need the notion of the discrete homotopy groups.
So what goes wrong with the
So
argument above if you try to do the same
oh yeah. So if you have this graph and you wanted to get to the constant map at 0 in any number of steps. So suppose you want to shrink everything to 0. So you might want to send 1 to 0 and then 2 to 1. But then 3, that means if you send 2 to 1, then you need to send 3 to 2, because otherwise you sort of pulling it open. And then that means that you need to send 4 to 3. But then that means that you're going to have a gap between 0 and 4, because 0 stays at 0 and then 4 goes to 3, but then there's no edge between 0 and 3. So that's sort of what's happening when you try to do this argument with C5. But I'll give a rigorous reason for why we know that's not contractible. So we're going to do this using a homotopy invariant. But yeah, this is sort of the heuristic for why this argument doesn't work.
But that wasn't a problem before when you sent 3 to 0
Yeah.
and 2 to 1.
So if you have this, then you might want to send 1 to 0, but then you don't need to send 2 to 1. You have the option of sending 2 also to 3. And then you would preserve all the edge relations. And keep 3 at 3 itself. And then in the next step, you go from 0 to 3 to just 0.
Okay, thanks.
Yeah, no problem. Yeah, so we have this intuitive idea of why C5 and bigger cycles are not contractible, but to really make that rigorous, we need the homotopy invariants. So let's define those. So for n greater than or equal to 1, we define the nth discrete homotopy group an of a pointed graph x comma x, and that's given as follows. So the way you define the set is by looking at graph maps out of the n-dimensional infinite grid graph. So it's an you take the I infinity, which is the infinite interval, take the box product with itself n times. So you have an n-dimensional cube, but it extends infinitely in both directions, in all two n directions, in fact. And then you're looking at graph maps out of this infinite sized n-dimensional cube into X. But then you want to have all the interesting things that are happening in only a finite region. So you impose the condition that at all but finitely many points in the domain, it has to take the value of the base point X. So I'm just calling it, it has to take the value X almost everywhere. What I mean by that is it does not take the value X at most finitely many vertices. Even though this graph is infinite, we're going to impose this finiteness condition. And then we're going to take this set and then we're going to quotient it by a relation, which is a homotopy relation. So we talked about homotopies between maps. So we're going to look at homotopies between maps, but with the added condition that the homotopies also take the value X almost everywhere. So that's basically a notion of a pointed homotopy. So it stays fixed at the base point, and everything that's interesting is happening in a finite region, even in at the homotopy. So that's how you define the nth homotopy group. So for example, if we look at the smallest one, which is the discrete fundamental group, so then you're just looking at maps out of I infinity, just plain I infinity, right? And then you're saying that outside a finite region, everything is constant at the base point. So those are essentially loops which start at X and end at X. Because if you look at only the finite region where the interesting stuff is happening, those are loops at X. So that's maybe builds an intuition for why this is the right definition. Or even if you compare it with the classical homotopy groups. So classical homotopy groups, maybe you're familiar with the definition out of the n-dimensional balls, but you can also think of them as maps out of n-dimensional cubes. So 0, 1 product with itself n times. And then you send the boundary of the cube to the base point. So that's what we're trying to do. And we're just using the infinite and this finiteness condition in order to allow concatenation. So if you wanted to take two different loops based at X, you want to be able to take a product of these loops. So those would give you paths from X to X, which are of a longer length. So by doing this finite sort of trickery, you're allowing this concatenation to happen. And that's actually exactly what the product structure on these groups are. The product structure is given by, you have these maps out of I infinity, but the interesting stuff is happening in a finite non-constant region. So you just take these non-constant regions, put them beside each other and fill the gaps with the base point X. So that's what you do for doing the product structure. And then for n greater than or equal to 2, you can use the usual Ekman-Hilton argument to show that these are actually going to be abelian groups. So it's sort of, we're just translating the definitions from classical homotopy theory over to discrete homotopy theory. And then we can talk about weak homotopy equivalences. So these are graph maps, which induce an isomorphism on every discrete homotopy group. So for every n greater than 0, the induced map F star is an isomorphism for every base vertex flux. So let's look at examples of this. So the first thing I said was that the discrete homotopy groups are a homotopy invariant. So that's what this example is saying, that if you have a homotopy equivalence, that's going to induce an isomorphism on all the homotopy groups. Now, in classical topology, you have that if you look at CW complexes, then the converse is true as well. So every weak homotopy equivalence between CW complexes is also homotopy equivalent. That means for every map that induces isos on the homotopy groups, you actually have a homotopy inverse. So for graphs, one of the open problems is that we don't know if there's a class of graphs for which the converse holds. So the first example to show that does hold for all graphs is the example of the unique map from I infinity to I0. So we've seen that you can't contract it in a finite number of steps, but it is a weak homotopy equivalence. It is weakly contractible, I infinity. And that's because when you look at homotopy groups of I infinity, you're mapping out of these infinite grid graphs, but it's actually all the interesting stuff is happening in a finite region. So it's going to map into a finite portion of I infinity. So that behaves just like a finite interval, which we saw is contractible. So all the homotopy groups of I infinity are going to be trivial. So this is actually going to induce an isomorphism on all homotopy groups. So it's weakly contractible. So we might think that the class corresponding to CW complexes might be just finite graphs. But actually, even if we look at maps between finite graphs, so for example, we can look at the map from the n+1 cycle to n. So I've given an explicit definition, but essentially what it's doing is collapsing one of the edges. So suppose you started with a pentagon and you send both of these vertices to the same vertex over here. So that's just collapsing one of the edges. That is a weak homotopy equivalence for n greater than or equal to 5. So we're going to see that that's going to be a result of a theorem that we'll see later, that it's going to induce an isomorphism on all the homotopy groups only when n is greater than or equal to 5. So we saw that 3 and 4, C3 and C4 are contractible. And we're saying that C5 is not, so the map from C5 to C4 is not going to be a weak homotopy equivalence, but all other cases, so C5 and above. So if you look at the map from C6 to C5, C7 to C6, etc., they're going to be weakly homotopy equivalent. And the reason this is not a homotopy equivalence is because if you look at any map that goes in the backward direction, you can't have a surjective map, so you'll always miss some vertex in the n+1 cycle. Essentially, you're imaging into something that's a finite interval, which was contractible. So any map that goes in the reverse direction is going to be homotopic to the constant map. So the composition cannot possibly be homotopic to the identity. Any possible composition that goes this way, right? So that's another example of a weak homotopy equivalence, which is not a homotopy equivalence, even though the graphs are finite. So we don't really know what is the class of graphs for which these notions are equivalent. But also we see that the notion of weak homotopy equivalence is really the one that's well behaved. So if we let W infinity be the class of weak homotopy equivalences, we have the slogan that, well, we asked what is discrete homotopy theory. We can really say that discrete homotopy theory is a study of the category of graphs equipped with the class of weak homotopy equivalence. So this relative category. Okay. So now we define these homotopy invariants, these discrete homotopy groups. But as we know, the homotopy groups are always easy to define, but hard to compute. So we really need some computational techniques to go ahead and compute these. So actually, one of the oldest results in this field, so going back as far as 1983, is that if you looked at the fundamental group, discrete fundamental groups of the n cycles, so that's going to be 0 if it's a 3 or 4 cycle. But if it's a 5 cycle or bigger, that's generally going to behave like S1. So, and your fundamental group is going to be Z. So that actually maybe proves that C5 and above are not contractible because you have this homotopy invariant, which tells you that it's different than a single point, right? And so the original proof is, I won't talk about the original proof, which goes into comparisons between graphs and spaces. I'm going to talk about a different proof, which sort of parallels the computing the fundamental group of S1. So to compute the fundamental group of S1, you need covering spaces and the theory of universal covers, and you look at deck transformations. So you need to do a similar thing where you develop a theory of covering graphs. And then you need to observe that this map from I infinity to Cn, which wraps around is a discrete model of the real line wrapping around S1. That is going to be a universal cover, but interestingly, it's only going to happen when n is greater than or equal to 5. This theory of universal covers, where we make sense of why it works for n greater than 5, but not for 3 and 4. That's in the first preprint that I mentioned. So it's called the fundamental group or the fundamental groupoid in discrete homotopy theory. So just some more computational results. So the next thing that after computing the fundamental group of S1, so the cycles, you want to ask about the Seifert-Van Kampen theorem. So maybe you want to compute the fundamental group of S2 or of the torus or things like that. So the question that the Seifert-Van Kampen theorem really asks is, when is a push-out square in the category of pointed graphs? So push-out square, if you're not familiar, is basically your X is the graph that you want to take the fundamental group of, and X1 and X2 are two subgraphs, and X0 is the intersection of the two subgraphs. So, and X is the union of X1 and X2. So if pushouts is unfamiliar, just think of intersections and unions. But basically, Seifert Van Kampen asks, when is the pushout square preserved by this functor, or the discrete fundamental group, which goes from pointed graphs to groups. So in topological space, it's fairly easy. We just need that these two maps are open embeddings from X0 to X1 and X0 to X2. In discrete homotopy theory, the hypothesis is quite tricky. It's not as easy as you might think. So we need to develop some language to talk about the hypothesis. So we're going to define these maps between intervals of different sizes. So you have these finite intervals of different sizes, and the graph map between them is called a shrinking map. If it is both order preserving, so remember the finite interval of the vertices are labeled from 0 to m or 0 to n. So we want the map to be order preserving, so it only goes forward or sticks at a point, and it has to be surjective. So in particular, it has to send 0 to 0 and m to n, right? So it's taking, and this only happens when m is greater than or equal to n, hence why it's called a shrinking. You can only shrink the finite intervals using these maps.
Hi, sorry.
Yeah.
Does the functor map into groupoids or just groups?
Groups, yeah.
Groups? Oh, okay.
Yeah, you also have an analogous of the discrete fundamental groupoid functor, which goes from unpointed graphs to groupoids. So that's going to come up a bit later in the talk. But yeah, there is a groupoid version of the fundamental group as well. Okay, so I want to introduce some notation. So you have this partial m sub comma n, which goes from this interval of size 2m plus 2n to this product of im box in. So that's basically an m by n grid. So it looks something like this, where this is maybe m and this is n. And what this map is doing is basically taking the 2m plus 2n sized interval and wrapping it around the boundary. So I don't think that's visible. So it's mapping it around the boundary, which is going to be, so it's going to map 0 and the last vertex of the same point that we started with, but that's what it's doing. And then we also need this map E sub I, which selects the ith edge out of the finite interval of size n. So which is just an interval of size 1. So we're just picking out the ith edge. And so we proved a version of the discrete version of the Seifert Van Kampen theorem. So as before, we consider push-out square in pointed graphs. And the first condition that we impose, because we're working with graphs, is that with groups rather than groupoids, is that all our graphs have to be connected. And the second condition is a bit more tricky, but it involves this notion of shrinking maps, is that every time you have this map out of I1 box I1, which remember was C4. So every time you have essentially what they're saying is you look at 3 or 4 cycles inside your graph X, which is the one that you're trying to compute the fundamental group of. There has to exist an m by n grid. So not just a 1 by 1 grid, but an m by n grid, together with a shrinking map, which compares the two boundaries. So this is the boundary of the 1 by 1 grid, and this is the boundary of the m by n grid, such that the following diagram commutes. So what this is saying is that this is the 3 or 4 cycle that you started out with, and you're subdividing this map out of 1 by 1 into a map of m by n. And what we mean by subdivision is that, so if you start out with this, you want to basically do something like that. So start out with just with the 1 by 1 grid and subdivide, and then so that the boundaries have to agree. So that's what this condition is saying. So capital H is the bigger grid, small h is a smaller grid, but they only have to agree on the boundaries up to a shrinking map. And there's a specific condition on this big m by n grid. So if you look at the m by n grid, what we're saying is that if you look at a particular cell, I, jth cell, so that's what this map is telling you, that's selecting the I, jth cell of this big m by n grid, each of those must factor through either x1 or x2. So if these two conditions hold, then the discrete fundamental group functor preserves the pushout, and you can use your Van Kampen to compute fundamental group of more complicated graphs. And this statement is quite tricky, and the only reason I'm pointing this out or spelling out this condition is because I want to emphasize the role played by these shrinking maps which compare intervals of different lengths. And this is going to be a recurring feature of discrete homotopy theory, as I saw during my research, is that this idea of wanting to blow things up and then look at the subdivided data, that's something that happens a lot in discrete homotopy theory. So this was the first instance where Van Kampen was the first instance where we saw it very explicitly, but we saw it again when we were trying to describe lifting properties. So just as for Kant complexes, you might have a lifting property. So you want to have similar notions for describing fibrations of graphs. So that's why I'm talking about this.
Is
Okay.
it, did you
Yeah.
say what exactly S is? Because there's many different ways of shrinking, right?
Yeah, so it could be any shrinking map. So there just has to be an m by n grid, and there just has to be a shrink map. It doesn't matter what the exact definition of the shrink map. There just has to exist one. The only condition is that it's order preserving, so it only goes forward, and then it's surjective. So all the entire boundary is covered. That's the only condition that we are imposing.
And what's the condition one again?
Or just that the graphs are connected. But that's just because we're looking at pointed graphs. If we're looking at the fundamental groupoid, you can basically drop this condition because you're not going to work with base points. So it doesn't matter. You don't need to have the connected graphs over.
So the condition is if I map any, I should think if I map any square into X, then I can sort of subdivide it into little squares where each individual square is either an X1 or an X2.
Exactly.
Which
Exactly. Yeah, exactly. Yeah.
What is in the proof of the Van Kampen? Something like that happens.
Yeah, the proof involves this induction on the length of paths. So we define paths out as maps out of IN and instead of maps out of I infinity, and then you can reduce everything to just edges. And then so the proof is kind of tricky. I don't want to go into it right now. I think that would be like a whole another talk just proving Van Kampen. Yeah, it's technical. Just as in classical homotopy theory, I think Van Kampen is a tricky proof. It's proving. Yeah. Yeah, the only reason I'm specifying this weird theorem is that things are not as neat as you would want them to be, even though the definitions were quite simple, often the results and the proofs are quite tricky. So another result that we have is that as a consequence of Van Kampen is that we give an explicit construction for such a theorem. So this is just an existence statement given here. It says that any group can be realized as the fundamental group of a graph. So in classical homotopy theory, when you think of graphs as just one-dimensional CW complexes, you can only realize free groups as fundamental groups of graphs. Whereas in discrete homotopy theory, you can have, say, torsion elements. So for example, we give an explicit construction of a graph with A1 as Z mod 2Z. So that's just a feature of discrete homotopy theory. And then you can actually extend that result. So this is not in our paper, but it uses the work of a lot of other mathematicians that if you started with an abelian group G and any n greater than 2, then you can take appropriate notions of suspensions. And then you can prove using, say, you need to develop a homology theory and then Mia-Vietoris and then a Urevich theorem. Using that, you can prove that it's going to have trivial groups below n, and it's going to have G as its n-dimensional discrete homotopy group. What's interesting is we don't know about the higher homotopy groups, so we don't have a method yet for killing the higher homotopy groups. But there's just sort of a proof sketch of what I've talked about. So you need to talk about appropriate notions of suspension because so in classical theory, suspension is taking product with the unit interval and then quotienting at 0 and 1. But here you can have intervals of different sizes. So it really matters which interval you take the product with. Depending on what n you want. So depending on the n, the size of the interval that you're taking the suspension with will change. And then you want to use Mia-Vietoris and cubical homology, and then you need a way to compare homology with homotopy groups. So this is a work of a lot of other mathematicians. So we just did the last step, which was just constructing graphs with a specified fundamental group. But then there's the discrete homology theory was developed by Barcelo, Capraro, and White in 2013. They also proved a discrete version of Mia-Vietoris. Then this appropriate notion of suspension, this idea was in this paper by Bob Love, excuse me. where he first looked at higher discrete homotopy groups of graphs. And then the discrete Hurwitz theorem was generalized to the correct extent in this paper by Daniel Carranza and Topology in 2022. Okay, so that's just a brief introduction to the subject. And I want
Can I
to
ask
talk a bit
a
about what
question?
the open problems. Yeah, sure. Go ahead.
So if you go, I was just wondering about that theorem that you mentioned about the fundamental group.
This
Uh,
one?
somehow the reason is like any like little triangle or a square, I should actually think of that as a surface.
Exactly.
So if I
Exactly.
just
Yeah.
do the usual construction and then I finish and then I just triangulate it at the end,
Yeah.
then it should
Right.
pretty
So
correct.
this paper that I've mentioned at the end, this 2022 paper, they actually Carranza and Kapulkin proved this conjecture which had been open in this field for many years, which was that we knew that for computing the fundamental group, it's sufficient to glue in a 2-cell every time you see a 3 or 4 cycle. But then there was the analogous theorem for higher homotopy groups was that every time you see a map out of I1 boxed with itself n times, so an n-dimensional 1 cube, you want to glue in an n cell. And you do this for all n, and then the topological space that you end up with will have the same classical homotopy groups as the graph that you started out, the discrete homotopy groups of the graph. So that was a open problem for a long time, which was settled in this paper. And so we're going to talk about this construction a bit. Okay, so just some quick remarks about open problems in discrete homotopy theory. For example, the first one is for what class of graphs do these notions of homotopy equivalence and weak homotopy equivalence coincide? And then we have this discrete version of Seifert-Van Kampen and Meyer-Vietoris. Then do we have, say, Freudenthal suspension theorem or the homotopy excision, or in the most general version, do we have a discrete Blake-Massey theorem? So we don't know that. Or for example, we had this graph which had a zero homotopy group 0 up till a particular n, and then it had the specified G as its nth homotopy group, but we didn't know about its higher homotopy group. So is there a way to kill those higher homotopy groups, giving us Eilenberg-MacLane graphs? And then if we had such Eilenberg-MacLane graphs, would they represent discrete cohomology? So these are a lot of open problems in this area where I think young mathematicians like myself can make a lot of contributions. So I encourage PhD students who are looking for problems to start looking into discrete homotopy theory. So now I'm going to get to fibration categories. So just a quick reminder or maybe just a quick introduction for people who are not familiar with fibration categories. So they're kind of analogous to model categories, just with lesser structure, because model categories can be sometimes too restrictive. So for example, the idea of CW complexes in topological spaces was that those are the objects which are both fibrant and cofibrant, right? So we don't have that class of fibrant cofibrant objects. So we don't really have a model structure in which you can do discrete homotopy theory, but we have the next best thing, which is a fibration category. So that's a category equipped with just weak equivalences and fibrations. And they're subject to certain axioms, just as your model category data is subject to certain axioms, but you don't have your class of cofibrations. And these are useful for computing homotopy limits, but not homotopy co-limits. So in model categories, you can compute both limits and co-limits, but in fibration categories, you get only half of it. But the homotopy category admits an isoscription. And just as you have equivalent junctions between model categories, you have a notion of exact functors between fibration categories. So these preserve the data that it needs to preserve in order to preserve homotopy limits and in order to induce a functor at the level of homotopy categories. So the definition isn't particularly important for this talk, but I guess it's just good to know that's the analog of equivalent junctions for fibration categories. Then the analog equivalent equivalence is the notion of weak equivalence between fibration categories. That is when the induced functor at the level of homotopy categories is actually an equivalence of categories. So that tells you when two fibration categories, which on the surface might seem to represent different homotopy theories, are going to be actually the same homotopy theories or equivalent homotopy theories. So let's quickly look at some examples. So the first example is the classical one of the category of topological spaces equipped with weak homotopy equivalences and Serre fibrations. So I've just defined self-fibration, which is defined using this lifting property. So this might be look a different than the usual definition of self-vibration, but it's really the same. It's just I've used a cubical version where you're looking at this is what's called an open cube. So if you're familiar with Kahn complexes and horn filling conditions or quasi-categories and inner horn fillers, this is sort of the cubical analog of that, but I'm just geometric realization of that. And this is the n-dimensional cube. And then that's the fibration category for homotopy types of topological spaces, hence the infinity up here. But then you might want to look at homotopy n types of spaces where your class of weak equivalences are maps which only induce isomorphisms on the lowest n discrete homotopy groups. And then you have an appropriate notion of fibrations called n fibrations. And over here now, instead of having these open box fillers in all dimensions, you only have the open box fillers in the lowest n+1 dimensions. And in n+2, you have the lifting with respect to the inclusion of the open box, not inside the cube, but the boundary of the cube. So that's going to give you a fibration category structure of n types of spaces. And another classical example is the category of groupoids equipped with equivalence of categories and isofibrations as the class of fibrations. So again, defined using these lifting properties. And then you have this classical theorem, which tells you that when you look at the fundamental groupoid functor from topological spaces to groupoids, that gives you a weak equivalence of fibration categories when you look at the fibration category for one types of spaces and groupoids. So this is an example of how you have algebraic models for homotopy n types of spaces, whereas you may not necessarily have algebraic, well, you don't have algebraic models for homotopy types of spaces. Yeah, so that's the very quick run through of what fibration categories are.
Sorry, Udit.
Yeah.
Those three examples do come from model structures, right? Example
That's
one
that's
is
true.
the underlying fibration category of the classical Serre model structure. Example two is a Bausch field localization, where you invert all the n equivalences.
Mhm.
And example three is also coming from a model structure, if I remember correctly, right?
Yeah, it's the canonical model structure on
the
groupoids,
canonical, right? Okay,
Yeah.
okay. But
So actually, that's
I'm
a
guessing
general
that
result that anytime you have a model category, you can look at the subcategory of fibrant objects. And so that when you restrict the class of weak equivalences and fibrations between fibrant objects, you get a fibration category.
yeah,
And
exactly. That's
similarly, if
right.
you had equivalent junction, you can look at the left functor, and that gives you an exact functor. And yeah, so
Okay,
but
and those
then
were examples
we're going
there.
to see examples of we're going to see one example of a fibration category or maybe more, which don't come from a model category. So
Got
there
it.
are
Thank
many
you.
others, but yeah, these are the ones in the context of discrete homotopy theory. Okay. So we're going to come back to this idea of discrete homotopy theory being the study of this relative category graph equipped with weak homotopy equivalences. And really, we saw the reason I talked about fibration categories is that a lot of computations are just made easier when you have this notion of fibrations, and then you can compute the homotopy category easily. So it really helps to have, well, if you can't have a model category, at least having a fibration category structure is really helpful. So I want to talk about what the fibrations corresponding to this homotopy theory would be. So they're going to be very similar to the Serre fibrations, a discrete analog of that. So for that, I want to introduce some notation. So you're going to have, we're going to start by looking at the n-dimensional cube of size m. So it's an n-dimensional cube where each side length is n. So the vertices in this cube are n tuples where each number is between 0 and m. And then you have an edge between two vertices, specifically when in exactly one coordinate, you only differ by plus or minus 1, right? That's your n-dimensional cube of size m. Then we can look at the boundary of that n-dimensional cube. So basically what we're doing over there is we're saying that for at least one direction, at least one coordinate, one of these xj's has to be either 0 or m. So it has to be one of the endpoints at one of the copies of im that we're taking the product of. That gives you the boundary of the cube. And then for taking the open box, you're going to that's going to be a subgraph of the boundary by removing one of the faces. So specifically, we're going to remove the face where xn equals m. So that's going to give you the one of the faces of the cube. which is going to be an n-1 dimensional cube. And in that dimension, if we impose the condition that we're only going to have the boundary of that n-1 dimensional cube, or at that face, that's basically an open box. So that's the cube, the boundary of the cube without one of the faces. So these are just analogous things for how we define the Serre fibrations. These are the discrete analogs of the objects. But now, because we have these objects in different sizes, the M was a parameter, and we're going to have these shrinking maps coming up again. So we're going to look at one specific shrinking map from IM plus 2 to IM. And that's going to be the shrink map that sends both 0 and 1 to the 0. And it's going to send n-1 and n to both n-2. So just collapsing the first and the last edges. And when you take the product of that map with itself n times, you're going to get a map from the n-dimensional cube of size m plus 2 to the n-dimensional cube of size m, where you're just sort of expanding or repeating a vertex at the end, or you're collapsing the outer boundary. And because the way we have defined this shrinking map, it's going to restrict to a map on the boundary of the cubes, and it's also going to restrict to a map on the open boxes, the corresponding open boxes. And you're going to have, well, if you drew these inclusions, all these diagrams are going to commute, all these squares are going to commute. Okay, so now we're ready to define fibrations. So graph map is said to be a fibration. Well, you would expect that as analogous to the Serre fibrations, if for in all dimensions and every your map had your F had the right lifting property with respect to the open box inclusion, but now the size becomes an issue. It's too restrictive to require that it has the lifting in exactly the dimension or exactly the size that you started out with. Instead, we require that, so similar to the Van Kampen theorem hypothesis, we require that instead of requiring a lift over here, we allow it to be relaxed by taking a bigger M greater than M, where these two maps can be compositions of these maps that we described earlier from the M plus 2 to M, but when you compose them, you can get any bigger size M, maybe just by different, they have to differ by an even number, but apart from that, basically, this is an existence condition. So that's all we require, that you can take the original lifting problem, relax the size by a shrinking map, and then require that this modified lifting problem has a solution. There exists a lift to this bigger rectangle rather than the square on the left. So that's the appropriate notion of fibrations. So again, we see that these shrinking maps are appearing. And so let's call the class of fibrations F sub infinity. And Daniel Carranza and Triskopolkin proved in their 2023 paper, the same one, the cubical setting for discrete homotopy theory revisited, that if you look at the category of graphs with weak homotopy equivalences and the fibrations that we defined just now, that actually defines a fibration category. So that really helps with a lot of computations. But naturally, when you have a fibration category structure for homotopy types of graphs, the question you might want to ask is this fibration category weakly equivalent to the fibration category of homotopy types of spaces? So there is a specific construction. So I mentioned in reply to a question that you can adjoin an n cell every time you have this n-dimensional cube that's sitting in your graph. So that actually gives you a functor from graphs to topological spaces. And you can actually ask about that specific functor, is that a weak equivalence? But I didn't want to define that functor, so I framed this question without describing the map. Just are they weakly equivalent? So is there a zigzag of weak equivalences between graph sub infinity and top sub infinity? And the reason we're interested in answering this question is because there are a lot of problems. Like, for example, we don't know what Blaker's mass is in the discrete version, right? We don't have that yet, but we have it in the classical version. And if we were able to sort of describe this weak equivalence of fibration categories, we'll be able to import a lot of classical results for free from the classical realm to the discrete realm without having to go through the, or at least get the statements, or maybe the proof you may not be able to import, but at least you might be able to get the translator statements using this construction. So, but that is actually a very difficult problem. A lot of experts believe that this should be true, but there's no proof as yet. And the work that I did with Triskopolkin in the second preprint, which was titled Homotopy N Types of Cubical Sets and Graphs, we tried to say that, if you can't solve a difficult problem, maybe split it into simpler problems that you can solve. So we saw that if we look at not at all homotopy groups at once, but only a finite, the lowest n homotopy groups, so the n types of spaces. We know that topological spaces have algebraic models, and then maybe we can ask if it's graph n or is it a fibration category structure for n types of graphs? That's the first question. And is it weakly equivalent to n types of spaces for a specified n? So that's just a strategy that we propose to attack this problem. So let me describe the strategy in more detail. So an n equivalence is a graph map that induces isomorphisms on the first n homotopy groups. And then your n fibrations are similar to this idea of these n fibrational spaces, just discrete analog, is that in the first n plus 1 dimensions, you have the same lifting property as you had for your fibrations, which is that you just relax this lifting property using these shrinking maps, and then you require that this relaxed lifting problem has a solution in the first n plus 1 dimensions, where this is the open box inclusion. And in dimension n plus 2, the only thing you need to change is that look at the inclusion of the open box into the boundary of the n plus 2 cube. So again, just the discrete analog of the classical result, except that we're using the string maps to relax the conditions. Okay, so we let f sub n be the class n fibrations, and we prove that this also describes the fibration category. So graph sub n equipped with, which is the category of graphs equipped with n equivalences and n fibrations, is a fibration category. And so now you can revise the question that we think is hard to prove or hard to answer. We ask a simpler question. So for a specific n greater than 0, is graph sub n weakly equivalent to top sub n? So is the homotopy theory of n types of graphs, is that weakly equivalent to the homotopy theory of n types of spaces? And we expect this to be more tractable because we have algebraic models, so we can use a lot of algebraic techniques. So just as a proof of concept, we're going to look at the n equals 1 case where we have the classical result that the one types of spaces are completely classified by the fundamental groupoid. So the first paper was about the fundamental group in discrete homotopy theory, or the fundamental groupoid in discrete homotopy theory. So different versions have different titles, but it's either group or groupoid. That's the only difference. But both of those versions have a notion of they define the discrete fundamental groupoid of a graph. And then in the second preprint, where we describe this fibration category structure, we were able to prove that, well, the discrete fundamental groupoid functor is actually a weak equivalence between these fibration categories. So your one types of graphs are actually equivalent to the canonical model structure on groupoids. And basically, as a corollary, we get that we have this zigzag of weak equivalences between graph sub 1 and top sub 1, where you have the discrete fundamental groupoid going from the graph 1 to groupoids, and then you have the usual classical fundamental groupoid going from top 1 to groupoids. And so that's a proof of concept in dimension 1. And for each dimension, you would actually have to develop an algebraic algorithm. So just like we have the fundamental groupoid, you might want to look at maybe the other algebraic models you have for n types of spaces, develop analogous result for graphs, and then do the same sort of thing. And that would hopefully allow you to maybe, if not get the full extent of the results, maybe at least partially. So for example, Van Kampen is only about the fundamental group. It's not about all the homotopy groups, it's just about one. So maybe for some of the results, you only need to look at the first n homotopy groups and not all of them together. So that's the strategy that we're proposing. And of course, this is just for the n equals 1 case. And for n greater than 1, it's still open. So there's a lot of work that needs to be done. And it'd be amazing if we have more people sort of working towards this. That's my talk. Thanks.
Thank you.
Good.
Are there any questions?
I do have a question. Thank you for the great talk. That's really exciting. You mentioned that this fibration category graph n or graph infinity does not come from a model structure. Is there an easy way to see that this doesn't jazz up to a model structure? Or
I don't remember exactly. There was a reason. I think it's something to do with, I think some colimits that you might expect, or homotopy colimits that you might expect don't, you can show that they don't exist. You can't,
okay.
yeah. So I think that's the way you prove that you don't have a full map.
Okay, certain diagrams that couldn't
Yeah,
have a
yeah.
colimit or okay. Great. And also about this last thing you mentioned about the case of n greater than 1. Do we have some ideas for n equals 2? Because classically in topology, already for n equals 2, there are different models, right?
Yeah.
There's some strict two groupoids, there's some bigroupoid of a space, there's a double
Yeah.
groupoid of a space, so you have these different variants.
I think, yeah.
What about on the
I
graph
think
side
there are
in the
also
discrete homotopy
cross
theory?
complexes. I think
Yeah.
something called cross complex. Yeah, there are a lot of models for when you go n greater than 1. And there
Right.
is
So
no
what's
canonical
the
choice
discrete
as such.
analog of that story? Do we have something for n equals 2?
I don't know yet. I would be interested to find out. Yeah, I think needs to be explored. Yeah.
Okay.
It's a good
Thank you.
question.
I have a question.
Yeah.
Yeah, so that was a really cool talk.
Thanks.
There was a statement a few pages back where you basically said that if you're given a group, you can cook up a graph such that its first discrete homotopy group is that group. So I wonder if this is related to the more classical classifying space construction where you look at the nerve of some category and then you construct a space out of that. So do you cook this graph up by maybe looking at some kind of cubical nerve in this case? How does it work?
Yeah, so the way we did this, wait, okay, is this the result
Yeah,
that you're
this is the
talking
one.
about, right?
Yeah.
Yeah. So the way we did this was, this is actually the construction of the graph depends on a choice of presentation for the graph group. So we choose a specific presentation, say G, S, and R. So S is the set of generators and R is the relations between the generators that you want to mod out by. And what you do is, well, we know that your C5s have fundamental group Z. And then so you can take a bouquet of C5s, one for each generator. And that would give you that would have the fundamental group to be the free group with S as many generators as you want in this. And then to mod out by the relations, you're going to glue in disks. So you're going to take something that looks like C5 box product with I1. So that's going to be a cylinder. And then you quotient out at, say, C5 box, say 0. So when you quotient so that gives you a cone on the cycle. So that's just a disk. So those are your disks. So you define your disk this way. So maybe call it D5-3 because, or not I1. I1 wouldn't work. So you need to take at least I3. That's because you want to be able to use Van Kampen. That's why you need to take big enough intervals. So in this case, I3. And then you basically glue in these disks for each relation. So for each relation, maybe of length, which might be a word of length, of some length, size of generators. So you need to describe a gluing map from the boundary of this disk to one of the cycles appearing in this wedge. And so when you glue those in, you will be able to mod out by the relations and end up with fundamental group being G. So that was the construction we used. I think we don't yet have a way of killing the higher homotopy group. So we know how to get the fundamental group just using Van Kampen, but we didn't really know how to kill A2 and A3, or even just compute. Do we even know that this construction already might be the Eilenberg-MacLane graph? Like, we don't know if that's true. So just computing A2. That's the problem with homotopy groups always. Is that you know how to define it. It's just very hard to compute. Yeah. Does that answer what you're trying to what you're asking?
Yeah, thanks.
Okay.
And I have a follow-up question. You were mentioning that we don't know exactly how to produce Postnikov truncations, right? We can't just say, I'm going to kill all higher homotopy groups by attaching tons of cells, right?
Right. Yeah.
Do we even know if that homotopy theory of graphs has Postnikov towers just for some abstract nonsense reasons, and we just don't know the concrete construction, or we don't even know if they exist in the background, those Postnikov towers?
I think we have. I think there's some graphs in which we know that the higher homotopy groups are 0. So, for example, C5 we know that if your graph does not have 3 or 4 cycles, then all your higher homotopy groups are going to be trivial. So that's a result that we know.
Okay.
So your C5, C6, and so on, these are Eilenberg-MacLane spaces for, these classify Z, the group Z. But we don't know it for, I think we had a construction for Z mod 2, but then we weren't able to generalize that for other groups. I think there's a PhD student of Folkmar Welker in University of Marburg. I think his name is Georg Will. I think he made a discrete analog of Milner's construction of classifying spaces, and I think he was able to produce classifying spaces for groups. But then I don't know if when we take suspension of those classifying groups, the homotopy groups that you killed make appear again when you take suspension. So there's a lot of complicated stuff happening.
Okay, and for instance, we don't have the analog of the classical fact in topology that if you attach an n cell, what you're doing is killing the attaching map in pi n minus 1 and not affecting the lower homotopy groups, but then wreaking havoc in higher homotopy groups, right? Because if we
so
had
we
that,
don't
we
know
could
what the
just mimic the
analog
same
of-
proof, right?
Yeah, so one of the reasons for that is that we don't know what n cells are, right? Because in graphs, we just has vertices and edges. So what do our n cells look like?
Oh, we don't even know that. What you just described are the two cells. We know how to attach a two cell, but not in higher dimension. Not like 3 cells,
No,
4
so
cells.
the construction that I was describing was treating the graph as a CW complex and then attaching topological n cells to it. So you end up with a topological space, right? So that's a functor from graphs to spaces, but we don't know how to do that in graphs. So we don't know how to...
Sorry, no,
Yeah.
I got that. I meant the purple thing still on the screen. That's a discrete
Oh,
2
right.
cell, right?
Yes.
Right,
Yeah.
right. So we don't have a discrete 3 cell, 4 cell, 5 cell.
And we have candidates, for example, your n-dimensional cube of size m might be one such candidate, but then we don't have the theorem that we would want by saying that, well, when you glue this in, that actually kills the homotopy group and preserves the ones that you want to preserve. Right?
I see. Okay, so we just don't have that on the discrete side.
Yeah.
Okay.
Yeah.
Okay. Thanks. Sorry if I may indulge. This is really interesting. I have another question about the different fibration categories, right? You started with F infinity, W infinity as a fibration category for the full homotopy type, and then you looked at the homotopy n type. The definition went by a bit quickly, but let's see, there are more n equivalences. So I would guess that there are fewer fibrations, right? Is it true that every n fibration is a fibration, or?
So the fibration category that we look at for n equivalences is actually not about left Gauss-field localization.
It's not about field localization. Okay.
Yeah.
Okay.
Because
So
if I remember correctly, if you wanted to do the left Gauss-field localization, you really want to have these basically these Postnikov approximations. You would want to have every graph would need to be weakly equivalent to another graph which has zero homotopy groups above level n. But we don't have that result here. So instead we needed to look at the other this. So there are two different. So I talked about one fibration category structure for n types of spaces, the classical one, but there's also the other one which comes from, as you said, the Gauss-field localization. So the one that I described, the top sub n, was not just the Gauss-field localization. Yeah.
Okay, this is great. That clears up also my previous question. I was thinking that maybe in the background, just having those different model structures, if they compared via localization, you could have various like fibrant replacements, things like that, giving you some kind of Postnikov tower, but that's not available here.
Yeah. So the way that these two, so one way to get these model structure for n types is one is by doing the left Gauss-field localization, and the other one. So there was a proof there's this paper from I believe the 90s, which did this construction for topological spaces and also for simplicial sets, n types of simplicial sets. And then, but they had a very explicit proof where they actually checked every axiom of the model structure. So we showed that this model structure that defines n fibrations this way, or well, not this is a discrete version, but the classical for topological spaces that is actually left transferred from the left boundary localization along the co-skeleton functor.
I see.
So
That's the
that
relationship.
these are related, like all these three model structures are related, but it's not, yeah, if you first take boundary localization and then transfer it along, wait, maybe it's not left transfer, I think it was right transfer along the co-skeleton functor.
Okay, I see. So
Yeah.
these end fibrations on the screen now, they're incomparable to fibrations, is that right? One class is not included in the other, or right?
Let me think.
Let's see.
I believe fibrations were a subclass of N fibrations. Yeah. Because
Oh,
for
okay.
fibrations, I think you had the lifting property in all dimensions, whereas for
Uh-huh.
N fibrations, you only have lifting properties in a few dimensions.
I'm worried
in the
about
first
the top degree. Can you scroll down a little
Yeah,
bit? Let's
right.
see.
So that it changes by having this boundary instead of the
Uh-huh.
just the box. Yeah. But I think that's taken care of because if you have the lifting property against the inclusion of the open box into the cube,
Mhm.
or maybe it's vice versa.
Yeah, I'm a bit worried about that one. I feel like the usual
No, yeah, that's right.
fibrations.
So if you
wouldn't-
have the lifting, so maybe let me just extend this. So if you if you're looking at this lifting property and you want your usual fibration to have that lifting property, well, you can extend that to the lifting property into the cube, the actual open box inclusion. And we know that that has a lift like this. And then so this composition will be this required lift for the one that you're looking at. So every fibration is an N fibration.
Okay. Okay, so fibrations sit inside the N fibrations. So, wait, is that right though? Wait, it feels wrong.
Yeah, I think we're used to the left boundary localization because that's the one we're more familiar with, and it goes the other way, I think.
No, but even in
yeah.
that picture, I'm worried about not having an extension of the bottom rightward map to the whole cube, right? Because you just started with a map defined on the boundary.
Ah, I see. Okay.
So can we
Right.
really invoke the original lifting property?
Oh yeah, maybe. Yeah. Yeah, I think oh right. I think you're right. I think it's only that your N fibrant your every Kahn complex is an N fibrant object. I don't think it's yeah, you're right. Sorry.
Oh, okay. Okay, yeah, that right. That would be right. But it's not a Gaussian locus. Okay, yeah, thanks. So that yeah, there's just a bunch of different fibration category structures in the background.
Yeah.
Okay,
Yeah.
thanks.
Hi.
So sorry, hi. I just wanted to make one more comment.
That's fine. Sorry.
Just proving this theorem about this being a fibration category. The way that we went about proving this was actually proving that there is an analogous model category on cubical sets. So I said that this paper which talked about this fibration category, or actually it talks about model category structures for n types of spaces and simplicial sets. So discrete homotopy theory is, for some reason, it's naturally cubical. It's because of the box product. It just makes sense to look at cubical sets. And so this preprint, which was called homotopy n types of cubical sets and graphs. So most of this paper is just building the model category on cubical sets, which is this using this boundary localization and doing this right transfer stuff. And that's also, I think, so we kind of, even though the simplicial version of this was known, this proof of doing the boundary localization and then transferring it, I think that's new. I think that wasn't recorded in. So as far as I a lot of work goes into just doing this for simplicial sets and also for cubical sets. So, and then finally we can sort of use the cubical nerve functor, which I haven't described, but the idea is that of gluing in these n cells every time you have this n-dimensional unit cube in the graph. And then that is what allows you to define this fibration category. Yeah, so sorry, that was just maybe a long aside of just describing what we're doing in this paper. Because I think if you see this talk and then you go and look at the paper, it might seem like they're not related at all for most of it, because a lot of it is just developing the abstract homotopy theory of cubical sets. So yeah, but yeah, that's the explanation. But I think I interrupted someone's question.
Hi, sorry. Yeah. Well, you mentioned earlier, like finding or developing an algebraic algorithm in order to find weak equivalences. Is that kind of what you were just describing with respect to gluing? I think. Like, does the gluing make things different
Oh, I just meant that
algorithmically?
I don't know if we have an algorithm. I just meant that when we look at n types of spaces, we have algebraic models. So I think Martin was talking about this a bit. Like we have strict n groupoids, and then we have, I believe, something called cross complexes. And there are various different models. Just like you have the fundamental groupoid, which is weakly equivalent to top sub one, you have these algebraic models for n types of spaces. And then, so instead of looking at these comparison between graphs and topological spaces, you can look at the functor going from graph to some algebraic category. So maybe n groupoids, maybe strict n groupoids or something else. So that's what I meant by having algebraic models. I I don't think necessarily it will be algorithmic because even if it's an algebraic invariant, I think there'll be a lot of uh, nuances to just defining these constructions. Yeah.
No problem.
So I think homology is where algorithms really become powerful. So I was describing Nathan Kershaw's work. So he's another student of Krista Perkin, so academic sibling. So he's working on discrete homology, which is the homology counterpart of the stuff that I'm talking about. And that is really where you can write Python code to compute homology groups. And so I think in my abstract, I mentioned that this has application to topological data analysis. So that's usually through homology. So you can look at so if you have this persistent homology, which is usually done using singular homology or singular homology, you might want to look at this discrete cubical homology of graphs. So if you start with a metric space, you can first construct a graph and then look at the discrete homology. So that's the homology area of things is where algorithms become important. Yeah.
Thanks.
I hope that answered your question.
Yeah,
Any
yes, thank you. No problem.
any other questions? If not, let's thank Udit again.
Thanks, Udit. That was a great talk.